Welcome to Data Science with EJD. In this video, we move on to autoencoders for dimensionality reduction with neural networks. We're talking about data science and we kept going until we got to machine learning. And where we see machine learning to be that area of data science, which where you have you know machines learning from data where you get to train where you get to train models on data and then and those models take a form of their own based on the data available from time to time. And as we drilled down, we discovered that there are different aspects, two major areas of machine learning, namely um supervised learning and unsupervised learning. Of course, there's also reinforcement learning. Maybe we'll get to that too. But we have supervised learning, unsupervised learning, and reinforcement learning. And supervised learning is where machine learns from label data. And when we talk about label data, we're talking about the kind of data where you have input and output data set. So the inputs are called features while the outputs are called targets, right? And then you have the unsupervised learning where you have unlabeled data. In that case, all there is to do is to discover patterns and trends and things like that from unlabeled data. So in that case, all you have are inputs. So from the inputs, you discover patterns, you see trends and things like that. But there's no association with a particular target like that, right? So, so we've been on with unsupervised learning all this while. For supervised learning, of course, we've seen the major algorithms. They are broadly classified into classification algorithms and regression algorithms. When it comes to unsupervised learning, you have things like dimensionality. I think we first started with clustering, where we saw things like k-means clustering, hierarchical clustering, spectral clustering. I think we came across uh, Gaussian mixture model and things like that. And then here we are talking about dimensionality reduction, the second branch, which is where we've seen things like power principal component analysis. I wonder why I call that power principal component analysis. And then we went on to do TSN, that's T distributed stochastic network embedding. And then in the last video, we actually saw another aspect of this, that's UMAP, that's uniform uh, manifold application and projection, And now we've come to the fourth part of this type of algorithm called autoencoders, and they're used for dimensionality reduction with neural networks, right? When we talk about deep learning, you're going neural networks. And apart from these two areas, right, where we've talked about, you know, dimensionality, first of all, clustering, dimensionality reduction, there's also associative is it associative learning or something like that? So which we are going to see by the time we're done with this, most likely. So the introduction, autoencoders, right? Dimensionality reduction aims to transform high dimensional data into a lower dimensional form while preserving essential information. So you have a data set, maybe with 16 features, and maybe you have like 100,000 data points like that. Especially the features are like 16, right? So what dimensionality reduction is doing for you is to bring it down to say two or three dimensions and still preserve as much information as possible on the original data. Traditional techniques of dimensionality reduction include principal component analysis, PCA, but these are linear models. But of course, we've seen nonlinear models like TSNE and UMAP. So autoencoders are a type of neural network provide when you hear the word neural, it should remind you of the brain network, kind of. I know that's really complicated and complex, right? So autoencoders is a type of neural network which provide a powerful nonlinear approach to non-dimensionality reduction. So of all the methods we've learned so far, talking about PCA, talking about TSN, talking about UMAP, and now autoencoders, only PCA is linear. The other three are non-linear. And from what we've seen so far, we discovered that UMAP is better than TSN. At least it's faster and it works better on large data sets. So what are autoencoders now? So let's focus on autoencoders, zero in on this. Autoencoders are unsupervised neural networks trained to reconstruct their input. So you give an input and it takes the input and reconstructs it, right? So by forcing the network to compress input data into a smaller latent space representation, the autoencoder learns efficient, meaningful encoders. And the core concepts are this. So you have encoder-decoder structure. So encoder map inputs X in D-dimensional real number to a compressed latent representation Z in the small d dimensional, where small d is less than d and z is f sub theta of x. And then that's the encoder itself. And then you have the latent space. This is the bottleneck layer output, which encodes the compressed features. So it takes something and it does the compression and then decodes it. Then the coder attempts to reconstruct the original input from the latent representation. So you have x cap equals g phi z, g phi of z. So the full autoencoder function is now x cap equals g phi into f theta, g sub phi of f of theta of x, where f of theta and g of phi are neural networks with parameter theta and phi. Then here we also have, the core. We are still talking about the core concept for autoencoders. We've talked about encoder decoder structure, and we also have the loss function, which is the mean square error. I mean, we've come across this previously. So the object is to minimize the reconstruction error between input and output. So you have an input x, and then you are going to have an output x cap, right? So the difference in error, the average difference in the square. So you have summation from I equals 1 to big N of the L is the I think this is what it's called the L2 norm, the norm xi minus xi cap, absolute absolute value of that part norm second norm of that raised to power 2. So and all of that divided by n. So here you are minimizing the loss. Minimizing this loss encourages the autoencoder to learn useful latent features. All right. So in advantages over linear models. So autoencoders can model nonlinear manifolds, and they are flexible architectures. They are deep and convolutional and recurrent. They can learn more complex feature representations than PCA or LDA. So we have done PCA, but we are going to do but we've not done LDA. In fact, you're going to like that. I think LDA is something about you know, title topic learning or something like that. We'll get to that very soon. So. Now let's look at the step-by-step Python implementation using MNIST. Of course, MNIST is that data set we've been using, that digits data set we've been using. That's one example. I think there are still other MNIST data like that, you know. So they are more like pictures, so to speak. So they set up, you import libraries and load data. So NumPy, Matplotlib. Now we are talking about TensorFlow.keras.layers, where you talk about inputs and dense, TensorFlows.keras. So, we are gradually drifting into, so TensorFlows. Let's see what exactly does TensorFlows do best. Is it deep learning or, let's see. TensorFlow makes it easy to create machine learning models that can run in any environment. Learn how to use this. TensorFlow is a software library for machine learning, artificial intelligence. Okay, so we are still in the realm of machine learning for sure. So here you're loading MNIST, a 28 by 28 grayscale images, X-train, X-test, MNIST.load data. Then you normalize pixel values to 0 to 1. All right. So you have x train dot as type floats 32 divided by 255. Same for the x test. Then flatten images, you have x train x test, So we do this. So this may take a bit of time because once you're beginning to work with images, things become a bit slower because you have a lot of processes to go through. Okay, this is done. Okay, I guess we're not at that point where it takes a lot of time. Now we want to define autoencoder architecture here. So, okay, I have not put the line numbers. It's always very helpful. Show line numbers. Okay. Okay, that is done. Define autoencoder architecture now. So input dimension, you have X-string or shape. You have 784 of that. Latent dimension, that's 32. Dimension of compressed representation. So imagine you're inputting 784 and you're outputting 32. That's a lot of work that has been done. So you have the encoder network. Input layer is equal to input shape, input dimension. So this input dimension up here. Encoder is dense 128 activation ReLU. This ReLU We've come across it a lot of times, or I've not taken time to find out what it is. Yeah, it is rectified linear unit. It's a popular activation function used in artificial neural networks. So it's known for its simplicity and efficiency in training deep networks. Value outputs the input directly if it's positive, otherwise it outputs zero. Okay, so it is rectified linear unit. Okay, so activation is rectified linear unit, input layer encoder for encoder, latent layer is dense, latent dimension. Activation is also RALU, then you have the encoder. For the decoder network, you have the same dense 64 activation, really RALU, latent layer, all that. And then output layer, you have a sigmoid kind of thing here. So this output matches input dimension. Then full autoencoder model. So you now have autoencoder model. Input is input layer, output is output layer. Encoder model for extracting latent features. You have encoder underscore model into input layer, output layer. So compiler to encoder with MSE loss and Adam optimizer. So we do this. So I suspect this is where this works as fast to good. Okay. So the next thing, we train the autoencoder, right? So you have history autoencoder.fit. This is where you train the model on the available image data set, right? You have X train, epochs 50. So you are going to have a bit of time trying to wait for these 50 epochs. And then you have the batch size of 256, and shuffle is true. Validation data, you have X test. The input is output for reconstruction, right? This one. So you have this input, and then this input is put there, and then it is reconstructed, and it gets an output. So we run this, and then we are going to 50 epochs. That is out of 50 done. So out of 50 done. So you can see that the loss is getting. So you have two types of losses, right? And the losses are getting reduced step by step, as you can see. Now we have. So we're on the 10th one, I think. Yeah. 10 out of 50. Okay. We're going 12 out of 50, still on the way. 13 out of 50. So you can see that the loss is getting reduced by each step, no matter how little. So the loss is getting down. So it keeps going until 50 epochs. So there may be a discussion about knowing the optimal number of epochs you should have to get the kind of results you desire, So but with 50 epochs, we keep going and keep getting better until we get there. So you can see the loss values are getting really reduced. Okay, so nothing seems to change here. So once everything is about the same, it's getting like it's not changing. Maybe we may be reaching some kind of convergence, but okay, we still have some reduction going on. Okay, so 39 out of 50, we keep going. 40 out of 50 now, 41 out of 50. So the values keep. Okay, you can see the loss values are looking up like almost the same for some epochs now. Okay, we are almost at 50. Okay. Yeah. So 0.80 is not changing. Okay, 7979. Okay, we are at the 50th epoch, and that's it. So all that is done now. So we have trained the autoencoder like that. So then we evaluate and visualize results now, having trained that. So we have decoded images is equal to autoencoder.predict x test. N is 10, plot figure is 20 by 4. Then we have the original images. So the original images from the image we have. So you have x plot subplot 2n I plus 1 plot image I am show. So you have x test I reshape 28 by 28. CMAP is gray. Plot title you have original. Plot axis is off. So that is the input. For the output now, that's now talking about the reconstructed images that you have done using the autoencoders. So we want to see all that too. So we have the decoded images, right? With the same shape and all that. So by the time we run this, we see something. So it just works, and then we see. So you can see that the original and the reconstructed look almost alike, right? They look almost alike. They look almost alike. So a fairly good job has been done on the image data set. Then the next thing is we want to extract latent representations. So to do that, we have x test encoded is encoder underscore model dot predict x test. So we want to print original shape x test the shape encoder shape x test dot encoder shape. So you have this. And then, yeah, so you see the original shape is 10,000 by 784, but encoded shape is 10,000 by 32. That's a lot of reduction done right there. So we have 10,000 data sets, but then the features have been reduced from 784 to 32. That's a lot of work done right there. So applications of autoencoder dimensionality reduction. So first of all, data visualization. So you can visualize clusters in 2D and 3D latent space. Preprocessing, you can compress data for faster downstream tasks. Anomaly detection, you can see large reconstruction error signals, anomalies. Denoising, autoencoders can be trained to remove noise. Then you have extensions and variants. Convolutional autoencoders for image data uses conv layers. I think that the convolutional layers for sure. Variational autoencoders, VAEs. You have probabilistic autoencoders generating latent distributions. Then you have sparse autoencoders that regularize latent space for sparsity. Then you have denoising autoencoders, which are trained to reconstruct clean input from noisy input. So probably that's what we've used up there now, denoising autoencoders. In summary, so looking at different aspects now, the purpose of autoencoders is to learn compressed representation of input data. The structure is you have encoder in the latent space, and then you have encoder goes to a latent space, and then we have a decoder. Then the loss you want to minimize reconstruction error MSE. Advantage, it can capture nonlinear data structures. Latent space, lower dimensional representation useful for tasks. Implementation easy with Keras, TensorFlow, which we used in this case, or even PyTorch. Then common use cases, dimensionality reduction, feature extraction, and anomaly detection. And that's how we've it's been for this particular video on auto encoders, right? So let me know how helpful this is for you, and if there's something you'd like me to try out or something you discovered while trying it out yourself. Don't forget you have access to all my code sheets by checking the description box. Just click on the description box. You can find the code sheets right there and work with them. So you can follow step by step as I do these things. Just as like I said, if you see any number somewhere, you can change it to see what happens if you change it, and that way you can see how the whole thing is working. All right. So if you have subscribed already, thank you for that. If you have not subscribed, please go ahead and subscribe and be sure to hit the notification bell so you can always get alerted each time a new video is released. On my channel, you can now become a member. There are 3 levels of membership, so check them out and see the associated perks to each level of membership. Right. Be sure to like and share this video and every other video you come across on this channel so that more people can have access to the great content I have going on here. So, like, come your way again. Keep doing data right. Bye.